So we're going to look at Mars, and Mars is of great interest to us for a number of different reasons. But the most important aspect about Mars is the fact that it has similar conditions, or had similar conditions to the Earth, and is thought to have had at one time the ability to maybe support not very complex, but simple life. Now, there aren't many places in the solar system that we think have conditions similar enough to the Earth to support life. We have, of course, Mars, the Galilean moons, in particular, obviously not Io, but Europa. And that is thought to be a world with a ocean underneath a thick layer of ice. Then Ganymede probably has a very, very deep mantle of water, but its layer of ice is much thicker, so any opportunity to ever access that is quite remote. Enceladus is another one. Enceladus is a small moon around Saturn, but it is thought that also it has a layer of ice over a liquid ocean of water, or at least a liquid pool of water. So the conditions there might be decent. Titan, not as much, but Titan, has a very cold surface, a very cold atmosphere. It's so cold that liquid natural gas exists on the surface, but it also has cryovolcanoes. This is where warm water comes to the surface and solidifies to become ice. So, perhaps Titan has a subsurface ocean of water. But Mars is the easiest to access because it's the closest by. Like the Earth, it's a planet. And although it ended up being somewhat different than the Earth, its early evolution was similar. So let's take a look at Mars and just compare and contrast, because that's usually the easiest way to approach these things. Looking at Mars, we're going to look at its primary characteristics. We'll talk about looking at Mars in the nighttime sky. Okay. We'll talk about its orbit, its atmosphere, which is really, this is very, very key to the prospects of life. We'll talk about the geology of Mars. Again, very key to life, the hydrological history of Mars. It's a fancy way of saying what was the history of water on Mars. We'll talk briefly about the interior of Mars. Talk about missions to Mars. There are so many missions to Mars, and then we'll summarize everything at the end. So if you want to look at this video and fast forward to any of these different points, that's sort of the order right here. This is sort of the table of contents. And, this will allow you to fast forward or rewind, depending on what you want to know about Mars. So overview, let's start with the general overview of Mars. It is the outermost of the inner planets. The inner planets go Mercury, Venus, Earth, and then Mars. It is 1.52 astronomical units from the sun. And this is one of the reasons why Mars is somewhat cooler than the Earth. Obviously, we'll talk about the greenhouse effects not being very, very effective. But at 1.52 astronomical units from the sun, okay, if you take the reciprocal of that square, okay, 1.52, and somewhere I actually do this, you square this, you will find out exactly how much less light Mars gets. Okay, thinking about this, the square root of 2 is roughly 1.41. So if I were to, essentially think about how much light, it would probably be about 1/3 to about a half the amount of light that we get here on Earth. Okay, so considerably less sunlight, okay? And just by rough calculations, again, less than half the amount of sunlight that we get here on Earth. And that's going to inherently make Mars cold. It takes 1.8 Earth years, or 1.88 Earth years, to go around the sun. Here's what's kind of cool, though. A day on Mars would seem very much like a day on Earth. It'd just be a half an hour longer. And you could actually get used to that with regard to your circadian rhythm if you lived on Mars. Of course, Mars does have 2 moons. That's the most of any inner planet. Earth is the only other one with a moon. But Phobos and Deimos are really quite unspectacular with regard to moons. Our moon is a considerable size. Phobos and Deimos are extremely, extremely small. Here's where people have not a great, this is where, many people's understanding of Mars is really lacking. We think of Mars as being just a little bit smaller than the Earth. It's considerably smaller than the Earth, okay? If we look at its radius, it's about 50% the radius of the Earth, okay? So if Earth were right here, and I'll show you a picture, Mars were right there, Mars would kind of look, maybe a little bit bigger than that. But the big difference comes in the mass. Mars has about 11% of the mass of the Earth, which means you would need about 10 Marses all put together to create one Earth, okay? That's going to be significant when we talk about its atmosphere, because first of all, less mass means less gravity, okay? And less mass means that the interior is cool enough so that there's no magnetic field, okay? We know in the Earth's interior, the convection of the liquid outer core creates a magnetic field that protects our planet. But Mars cooled down too quickly, so perhaps its core is completely solid and can't generate a magnetic field as a result. Also, its gravity is low, and these two things lead to the fact that most of its atmosphere has since escaped into space. So again, that's what Mars looks like next to the Earth. 53% of the radius, okay? 15% of the volume, but again, about 11% of the mass. All right. If we compared Mars to Venus, it'd pretty much be about the same comparison. Venus is a little bit smaller than the Earth. So again, Mars is going to be considerably smaller than Venus. Mars is larger and has a greater mass than Mercury. However, Mercury's higher density makes its surface gravity greater than Mars by just a very small amount. So of all the inner planets, you would weigh the least on the little red planet. And again, here's comparing the masses to one another. Earth and Venus compare very similarly, or they are very similar, at least in terms of mass and the rest of the interior. And then Mercury and Mars are pretty much at the bottom right here. Mars has 2 times the mass of Mercury, okay, about 13% of the mass of Venus, and about 8.7 times the mass of the moon. So if you're thinking about the comparisons between Mars, Earth, and the moon, the Earth is many times more massive than Mars compared to Mars to the moon. It's also, its density is lower. It has less iron in its core. Earth's density is 5.52 grams per cubic centimeter, and some of that comes from gravitational compression. Mars is considerably lower, 3.93 grams per cubic centimeter. Let's talk about the orbital properties of Mars. If we remember going back to the story about Tycho Brahe, oops, I always have a tough time spelling and thinking at the same time. So Tycho Brahe versus Kepler, Johannes Kepler. We know that Tycho observed Mars and found that its data was very, very strange. The reason why I found the data to be very strange is Mars has one of the more elliptical orbits of all the inner planets. Okay, it has a very oval shape to its orbit. So does Mercury to some extent, but Mars has a high eccentricity. Although it's still fairly round, it's 0.093. And that was enough to throw off Tycho. Again, its orbital period is about 1.88 years. That's 687 days. So a year on Mars would be longer than a year on the Earth. Again, 1.52 astronomical units from the sun makes the amount of light much less. What's interesting is with the elliptical orbit, Mars's high eccentricity means that basically it spends some time much closer to the sun and sometimes slightly farther from the sun. Again, Earth's eccentricity is, 0.027. So Mars is more than 3 times greater in its ellipticalness than Earth, if you want to use eccentricity as a measure. So this means that in the southern hemisphere, we get more extremes. Summer occurs near perihelion, and winter occurs during aphelion. So that means the summer is warmer in the southern hemisphere and colder in the winter, warmer in the summer, colder in the winter, in the southern hemisphere than it is in the northern hemisphere. So we get much greater variations in the polar caps, whereas in the summer southern hemisphere, we'll get a bigger buildup of carbon dioxide ice or dry ice. Those extremes aren't as great in the northern hemisphere. Northern polar region, yeah. Looking at Mars in the nighttime sky, it experiences retrograde motion. Basically, as we pass Mars in its orbit, so if you're close to opposition, which means Mars is on the opposite side of the sky as the sun, it rises at the same time that the sun sets. So at opposition, Mars is actually going through what we call this retrograde loop. All right, so it sort of goes east, then it switches in a westerly direction, then it goes east, and that's just us passing it in the orbit. Okay, the retrograde motion of Mars was used by Ptolemy, of course, to explain his epicycle model, or used it to basically create the foundation for his epicycle model. And yes, Mercury and Venus would go back and forth in the sky also, as would Jupiter and Saturn, but Mars's retrograde motion was the most pronounced. It's pretty close to being in the plane of the solar system. If you took the average orbits of everything, Mars would only make about a 1.8 degree inclination with regard to all the planets. So like all the planets, Mars, when we look at it in the sky, is going to remain close to the ecliptic. It's not going to go very far from the path of the sun across the sky, being in the plane of the solar system. Here's another thing that's interesting. The axial tilt of Mars is almost identical to the axial tilt of the Earth. Okay, so it's going to experience seasons just like the Earth, and it's going to also precess, or its axis is going to rotate as time goes by, just like the Earth. And again, solar day on Earth, 24 hours. Solar day on Mars, 24 hours, 37 minutes. Nearly identical. What about Mars's atmosphere? When we look at the inner planets, we have Mercury. We talked about that earlier. Mercury has no atmosphere. Any gas that really sticks around it would be at best called an exosphere. The gas which is gravitationally held near Mercury eventually drifts out into space. So we can't really say there's any real atmosphere there. Venus, of course, has an atmosphere which is 100 times greater than the Earth. Okay. And of course, the Earth is at 1 atmosphere. That's how we define the atmosphere at sea level. Mars is roughly about 1/100th the pressure and density of the Earth. Okay, so again, these are rough approximations. Okay, Mercury again is pretty close to 0, no atmosphere. Venus, 100 times more atmosphere, because unlike the Earth, which had locked many of its volatiles to become the ocean, and also carbonates, locked a lot of the carbon dioxide as carbonates and rocks. Venus's gases, some leaked off into space, but most are still held fast by Venus's gravity. If we were to boil off all the oceans and melt all the carbonate rocks, we would end up with an atmosphere similar to that of Venus. But Mars, at 1/100th the density and pressure of the Earth, one question would be, well, how come Mars, if it has no ocean, why doesn't it have more atmosphere? Well, that's the story that we're going to tell here. Most of Mars's atmosphere has leaked into space. Mars has no magnetic field to protect it from the solar wind, and it has very little gravity to hold on to it. So even though Venus doesn't have the magnetic field, its gravity is strong enough to retain most of its atmosphere. Mars, however, can't shield its atmosphere from the solar wind and can't hold on to it due to its weak gravity. So the atmosphere of Mars, 95% carbon dioxide. Even if it were the same pressure as Earth, you would suffocate very quickly. There's almost no oxygen in it. The rest of the gases are mainly nitrogen, argon, and water vapor. As we said, about 1% of the density and pressure of Earth, and not much of a greenhouse effect to keep the planet warm. Again, here's just looking at the composition. Tiny, tiny trace of oxygen. Not enough to support life, okay? At least not eukaryote life. Trace amounts of carbon monoxide, that's not good for us, and trace amounts of methane. So the atmosphere of Mars. Mars, Venus, and Earth all probably started with similar atmospheric compositions. We know the early terrestrial planets were dominated by thick atmospheres, which were rich in water vapor and carbon dioxide. Venus, as we said, has a very dense atmosphere, but some of the water was lost into space due to photodisassociation and due to the solar wind. Earth converted most of its water into oceans and buried most of the carbon dioxide into carbonate rock, thanks to the ocean. But Mars has very, very little density to its atmosphere, okay? If you're to go to the total number of moles of gas in the atmosphere, you'd come up, given Mars' smaller size, with an even smaller fraction. And again, 1/100th of a hundredth tells us that the density of Mars' atmosphere is 1/10,000th that of Venus. So right now, Mars is not really capable of supporting human beings without environmental suits. Now, even though the atmosphere is very thin and gravity is low, high winds can create very significant dust storms. Now, on Earth, most dust storms are fairly regional, okay? We get Sahara dust clouds that come over every once in a while across the ocean, but they don't encompass the entire globe. On Mars, however, dust storms tend to start in the southern hemisphere during the warm summers and end up engulfing the entire planet. So, dust storms really can change the appearance of Mars quite dramatically. The surface of Mars is covered with what we call regolith. This is a fine, powdery dust. And with the right conditions, this dust will get kicked up and spread all over the place. Here's a dust storm in 2001. You can see the planet. There's very little surface features. You can see a little bit of darkness there. But the entire planet experienced this obscuring event. And again, the dust absorbs sunlight, heating the atmosphere and increasing the wind speeds. And we always see the dust storms start in the southern hemisphere during the summer months. Remember, Mars is closest to the sun. It's at perihelion when the southern hemisphere is pointed toward the sun. Here's another image of right before the dust storm and during the dust storm, so you can see clearly. Okay, these are the same regions right there. There's crater right there. There's that same crater. You can see that it can really obscure the surface. What's interesting here is we can also see high altitude clouds in this other image. And of course, another dust storm happened in 2018. This is probably the reason why Opportunity, the rover, failed, because both Spirit and Opportunity had solar panels. Spirit's failed first. Its solar panels got too covered with dust. It couldn't produce enough electricity to keep going. During the 2018 dust storm, Opportunity, the second rover, also got covered and became too cold to continue to operate and pretty much ended. Now, the Martian surface pressure actually goes up and down. Most of the atmosphere is made of carbon dioxide, but carbon dioxide can freeze, making dry ice. As the dry ice becomes solid, we call this process, I should say, as the carbon dioxide goes from a solid to a gas, we call this sublimation. As it goes from a gas to a solid, we call this condensation. Okay, so when the atmosphere gets colder, it condenses, forms carbon dioxide caps at the poles. When Mars warms up, carbon dioxide returns to the atmosphere through a process called sublimation. So you can see here how the atmospheric pressure goes up and down, okay? And again, that corresponds to the different seasons. When it's summer in the southern hemisphere, we get a higher pressure. When it's winter in the southern hemisphere, the carbon dioxide will condense to form these ice caps. Mars also has convection in its atmosphere, convection cells, what we call Hadley cells, in each hemisphere, just like the Earth does. However, with a less dense atmosphere, the convection isn't quite as vigorous. So the weather on Mars is going to be, well, there's not much atmosphere there, not as intense. Another interesting find is methane. Methane is the primary component in natural gas. And on Earth, methane is produced as organic matter decays, okay? So methane, or natural gas on Earth, is considered to be a fossil fuel, comes from dead plants decaying. On Mars, we don't know where this methane is coming from. One exciting idea would be that perhaps this methane is produced by some Martian microbes, right? However, there are non-living processes that can also produce methane, So methane is not necessarily proof of life. But what's interesting is we see methane occur in higher concentrations in some parts of the planet and lower concentrations in other parts of the planet. Because UV light will break down methane. Methane cannot stay in the atmosphere for very long. So again, what's producing this methane, we're really not sure. Here is a map showing methane abundance at a particular time of the year. And we have, again, not a great understanding of why this methane seems to be leaching out of the surface. Okay. Here's one idea. Mars is thought to be still somewhat geologically active, not to the extent that the Earth is, but there is some geological activity. We think that as water seeps into the interior, the hot groundwater will interact with other materials, okay? And we can actually synthesize methane from carbon dioxide or carbonate rock and water, but we're not quite sure what sort of non-living process would produce methane. So the presence of methane could be due to, again, volcanic activity. There's other evidence to support this theory because we know that some of the volcanoes show limited activity within maybe the last few million years. A more exciting conclusion, of course, would be that these are actually living organisms that are creating this. But you can't say for sure unless we actually find the organisms producing the methane. Both theories are exciting because we thought Mars was volcanically, biologically dead, but the methane seems to be coming from someplace. Now, where did Mars's atmosphere come from? The general thought is when the inner planets formed, they formed close to the sun where it was hot, and that most of the planets formed from rock and metal, okay? It wasn't until the late bombardment that material from the outer solar system, primarily from the asteroid belt, was sent hurtling toward the inner planets. Like many of the terrestrial planets, pieces of these asteroids were very rich in water. So they're highly hydrated. The original theory was, oh, well, comets could crash into the planets and bring water that way. However, the isotope ratio for the water found in comets doesn't match what we find on the terrestrial planets. So we needed another source, and we were pretty sure that this would have come from just these water-rich bits of asteroid. All right. For instance, we know Ceres, which is the largest of all asteroids, has a mantle of ice water. So again, Mars has lost most of its atmosphere. We know this because, and we'll talk about this in more detail than you probably like, the isotopes of the different gases that are present in the atmosphere are richer and heavier isotopes. If the atmosphere is escaping into space, it's the heavier isotopes that are generally left behind in higher concentrations. So for instance, if you have a heavy isotope and a light isotope, maybe you'll lose 99% of the light isotope and 98% of the heavy isotope. If you're only left with 1% of the lighter isotope, that means you can have nearly double as much of the heavier isotope, given that type of scenario. Okay. And again, we can study special types of meteorites known as chondrites. Okay. Especially carbonaceous chondrites are very, very rich in water. And all pretty much all meteorites come from broken pieces of asteroids. So the asteroid belt, being more than 3 times further from the sun, could have accumulated the water and then brought it back to the inner solar system. Now we're going to go through a lot of these diagrams with different isotopes, and it's probably at a higher level than we really need to go for in an introductory course. But again, the main point here is, how do we know Mars didn't just have a weak atmosphere all the time? Again, if you have a large number of heavy isotopes, compared to light isotopes, because the solar system came about from all the same material, a high ratio of heavy to light isotopes is indicative of most of the atmosphere being lost into space. Now, again, there is a certain type of chondrite that we think could have been a great source of material that would have brought back water to the inner planets. Okay, it has the right ratio of certain isotopes of oxygen, such as oxygen 17. The pattern of noble gases, pretty much matches the, from all the missions, they're pretty consistent. N2 and CO2 abundances are about the same as we would expect. And here again, look, nitrogen, there is 1.62 times as much nitrogen 15 to nitrogen 14 on Mars as there is on the Earth. And what does that mean? Mars has lost significantly more of its atmosphere than the Earth has. And again, more than you really need to know, nitrogen 14 is heavier than nitrogen 15. So the nitrogen 15 is going to escape into space more often, okay? When nitrogen goes to the top of the atmosphere, it gets hit by a photon. That's what this little fancy thing says right there. H nu is actually the energy from a photon that ionizes nitrogen. The nitrogen then will dissociate into different atoms, becomes lighter and lighter, and it's easier just to sweep that off into space. Again, without a magnetic field to protect it, once these atoms get high into the atmosphere, they can just drift off on their own, or they can get hit by the solar wind and get just eroded into space. Let's skip through some of this. And again, Mars has the largest nitrogen 15 to nitrogen 14 ratio in the solar system. What this indicates is Mars, of all the inner planets, has lost the most atmosphere. Oxygen too, oxygen also escapes into space, okay? Typically oxygen, if it were in diatomic form, absorbing energy from the sun would just break it down further. Carbon dioxide also can dissociate into its atomic species. It's actually shown carbon monoxide. And again, it doesn't take all that much energy for this to escape into space, but a lot of the oxygen, instead of just making its way into space, is also thought to have reacted with the surface. So heavy gases can be lost from Mars, not just light gases like hydrogen and helium. We call this process sputtering. Basically, we can imagine that these particles, which are nuclei of atoms, just part of the solar wind. A lot of junk coming in there. A lot of them protons, a lot of them helium nuclei. They come in with a very high velocity. And when they hit, the gas molecules from the atmosphere, they can give them enough energy to just knock them into space. And again, Mars has no magnetic field. That solar wind comes very, very close to the surface. On the Earth, however, we have a shield. We have this magnetic field that prevents these particles from making their way in. And thus our atmosphere is pretty much protected. Now, the MAVEN spacecraft, which is still in orbit today, has studied the loss of atmosphere due to the solar wind. And again, it's not that the solar wind makes it right down to the surface. There's actually a bow shock that results, much like when a boat travels through the water, produces a wake. The same thing happens here. But here is basically the measurements taken by MAVEN showing that when there's low solar wind pressure, that the sunward side of the ionosphere is nice and thick and protective, and most of the atmosphere is going to be okay. You know, some will be lost into space, as is shown right here. But when the solar wind becomes very active, the ionosphere thickness gets much weaker, and more of this gas can escape into space in this little tail right here. Again, there is no magnetic field to prevent this from happening. So Mars, it's been leaking its atmosphere into space for billions of years, okay? It may have had a magnetic field at one time, but it doesn't right now. Now, Mars, again, we'll talk about this. Mars was once much warmer. It had liquid water at one time. And where did this water go? Because we look at the planet, it looks pretty dry. Well, the first thing that some of the water did is that as Mars lost its atmosphere, much of the water simply just froze into the soil. And it got covered up with more and more regolith. There's a very large concentration of water, not just in the polar caps, but frozen below the surface in the Martian soil. Okay. Additionally, we know that water would have been lost into space without a magnetic field. Any water vapor that would have drifted high into the Martian atmosphere would have been subjected to ultraviolet light. The ultraviolet light would then have broken down the water into hydrogen and oxygen. The hydrogen, being very light, would escape into space, and the oxygen, being very reactive, would probably react with different minerals that are in the soil. So yeah, Mars was once warm and much wetter. Today, much of that water is either frozen into the soil or is completely lost into space. All right. And again, hydrogen is really easy to lose. Okay. Hydrogen can escape into space by two basic processes. One, it just gets enough energy and speed and just escapes. Okay. The other one is the hydrogen atoms are hit by solar wind particles and they're knocked into space. Okay. So hydrogen is one of the easiest things to just send off on its way. Now, oxygen can escape or be lost either by reacting with minerals on the surface, or again being hit by solar wind particles and getting enough momentum to break free of Mars's gravity. So this is a good diagram that summarizes what's happening here. Okay. There's no ozone layer protecting Mars's atmosphere from the UV light. So ultraviolet light will hit water molecules in the atmosphere and break them apart. The hydrogen will be light enough to escape into space. The oxygen will be reactive enough to react with minerals in the soil. So that's one way to get rid of the water. Another way is, well, solar particle will come in and break a hydrogen free. Okay, hydrogen goes off, oxygen is reactive enough to react with the soil. Let's talk about water on Mars. We're going to talk about what it's like currently, then we'll talk about what it was like at one time. Hydrology. Now, this is the 2001 Mars Odyssey gamma ray spectrometer. Neutron and gamma ray studies have clearly showed that in the polar regions, there's a high amount of water. Neutron spectrometers basically look at the neutrons which are naturally produced, and since they inelastically collide with the light water molecules, you'll get a very low reading of scattered neutrons in the polar regions where the water is very thick or where the water is very concentrated. Gamma rays work a little bit different, but the results are pretty much the same thing. We know that in the polar regions, there's a lot of water which is trapped in the soil. Okay, and that doesn't even include the ice caps, which are further up here. So as Mars got cold, the water could no longer remain liquid, it started becoming solid. As it turned into a solid, it froze itself into the soil, and that's where it remains trapped today. This is definitely not. Our first pictures of Mars came in 1971, and then in 1976, Viking, which was both an orbiter and a lander, took lots of pictures of the surface. And what was clear was there's lots of erosion evident. This is an outflow channel, and this was taken by the Viking orbiter sometime around 1986. Now here you see a nice round impact crater. We see these on the moons. On the moon, there's no water on the moon, and there probably never was water on the moon. But clearly, in this structure right here, which could have been an impact crater, we can see that water has flowed out here. And we can see the channels that it's carved as it went from one location to another. Okay, that water had to be there for a long time for that to happen. All right, so going back to the 1970s, we knew that water must have existed at one time on Mars. Here's another view of clearly erosion channels by the Viking orbiter. And another one. It looks very similar. This is the type of structure, if you've ever seen a satellite image of a canyon, like the Grand Canyon, you see a lot of this dendritic-like structure. All right. And here's another one. Again, pretty substantial here. So all from the Viking missions, we see this this flow of water. Here's more recent evidence. This was probably taken from oh gosh, not the Mars Odyssey. Oh, maybe. But in any case, again, we can see this channel right here flowing into this crater over here. More of the same. Here we have a cutoff channel where, almost looks like you have this delta, okay, and then some cross cutting down here in this area right there. Now, what's strange is we even see some of this activity today. These gullies that we see, which are on a crater rim, this is the rim of the crater right here, actually change with time, which seems to indicate that there's still liquid water, but not necessarily the way we would think about water, okay? If I took a glass of water on the surface of Mars right now, it would simply evaporate or boil off, even though the temperature is quite low, where most of it would be lost to the atmosphere. What's remaining would simply freeze to form ice. But we now know that when the water mixes with the soil, it can remain in somewhat of a liquid state. So what you're seeing here are really mud flows, all right? Something warms the water enough where the soil and water mixture becomes liquid, and it'll flow, given enough time. But of course, in most of these cases, the expectation would be the water, if it came to the surface, would evaporate quickly or simply freeze. So how did the Martian valleys form? We've known about these Martian valleys cut by these channels of water, since the 1970s. So over 50 years, we've known about these. But we know today there's just not enough water to produce. So we've come up with some basic models for what we think Mars might have been like at one time. First model is this. Mars was warm very early in its history, okay? It had plenty of water, and that the water that was necessary to cut these channels would have come from basically erosion due to rainfall, okay? The second model is, no, Mars wasn't that warm. It's always been cold. That it warmed up sporadically, maybe due to an asteroid impact. And when it got warm, the water would flow. And then after the effects of the impact, basically died away, Mars would be going back to the way that we see it today. The second cold Mars model would be Mars has been cold all of the time. Groundwater reserves were recharged by vapor diffusion from a subsurface aquifer, okay? And basically, a lot of this could have been enhanced by heating just from, geological processes, okay? So what model do we favor right now? Well, we'd like to think that Mars was warm and had plenty of water at one time, okay? That would be the best to support life, okay? But can we rule out these other two models that, it only heated up some of the time, or no, there's not really much water. The water is coming from these underground springs, and once it gets to the surface, it pretty much dissipates. Now, let's do some compare and contrast to the Earth. The Grand Canyon on the Earth required about 17 million years to form, okay? During this time, we think that about 5 million meters of rain should have fallen on the Colorado Plateau, assuming about 30 centimeters of rain per year, and essentially cut the Grand Canyon that we see today, all right? Here is a Martian valley, which is very similar to the Grand Canyon, all right? So we knew something big like the Grand Canyon has easily been cut into the surface of Mars. Now, by contrast, those who've argued that Martian valleys could have formed in a cold environment assume much lower volumes of water. that if Mars would sporadically warm up, okay, from an impact, or maybe some subsurface water would come up and flow for a while, that would indicate about a precipitation amount of 50 to 500 meters. Okay. What I'm saying here is cold doesn't seem to work. Okay. Cold produces too little water. That's wrong by about a factor of 10,000 to about 100,000. Okay. So basically, we had to have quite a bit of rain to cut these types of canyon structures that you see here. Well, maybe Mars is so easily eroded that we could cut these channels just because the surface is very, very weak. Well, comparing what we see out in Colorado, what we see in some other places, the soil erodibility on Mars should be pretty much the same as what we see here on Earth. So it's not like Mars is really any different, right? Its gravity is actually lower, so it makes it harder to erode. But it's not like the soil, suddenly just erodes away even with a tiny amount of water. So that can't be the explanation. So the impact hypothesis for the valley formations, for these canyons, just would only work if Mars's surface consisted of very, very weak, loamy sand rather than the types of rock and soil that we see on Mars. Okay. That's not what Mars is made out of. It's not made out of this loamy sand material. It's made out of similar materials to that that we see. So cold Mars models just don't work. Okay. From what we know, the copious amount of water really requires a warm early Mars. Essentially, Mars's early climate was very Earth-like. All right. The water needed to carve out the valleys came from rainfall, same processes that we see on Earth. How could early Mars have been kept so warm? Here's our problem. Even if Mars had a substantial atmosphere early on in its life, it is significantly farther from the sun than we are. It's 1.5 AUs. And as I said before, at 1.5 AUs, you are getting to a considerably considerably less amount of sunshine. Okay. If I take 5.2 and I square 5.2, I get about 30. All right. And then if I take the inverse of that to see how much the light compares to, oops, I did this wrong. I don't get 30. That's wrong. I take 1.52. I'm doing this on my calculator right here. I get 2.3 if I square it. If I take the inverse of that, I get 0.43, which means that Mars only had about 43% of the sunlight that reaches the Earth. Okay. That shouldn't produce liquid water. So to answer this question, we first need to think about how Earth remained habitable even in its early history. We know at some points, even though the Earth is closer to the sun, there are periods where it completely froze over, periods that we call the snowball Earth. This happened when cyanobacteria released so much oxygen into the atmosphere that there's very little CO2 and very few greenhouse gases to keep it warm. Okay. The other aspects we've got to consider here is that the sun was actually less luminous than it is today. Okay. All right. Earth's got some things going for it that the planet Mars does not. Earth has what we call feedback mechanisms, which allow it to actually adjust its climate. Okay. There's the carbonate silicate cycle. And this happens on Earth where if the Earth becomes too warm, it rains more. And that dumps more CO2 into the oceans, which forms a carbonate ion. Carbonate ions then react with alkali earth metals like calcium. They get buried into the interior of the Earth. And this basically is a very good way to take CO2 out of the atmosphere and decrease the amount of greenhouse warming that we have. Okay. Now, if the Earth gets too cold, we have the carbon dioxide basically building up in the atmosphere. Let's say, for instance, oh, okay, I make Earth so cold, I've got this big sheet of ice covering it, okay? Now there's no more carbon dioxide going into the ocean anymore, right? So I don't form carbonate rocks. I don't bury the carbonate rocks. All the CO2 that's in the atmosphere stays in the atmosphere. But in addition to that, things are going to warm up. Why? Because volcanoes, even if they're ice covered, are still going to be active. They're going to dump their CO2 into the atmosphere. So this is going to cause the temperature to go up as the greenhouse gases build up more and more. So basically, if the Earth gets too warm, we get more CO2. I'm sorry. Let's go the opposite direction. If the Earth gets too warm, we get less CO2 due to erosion and the carbonate silicate cycle. If the temperatures get too cold, I'll get more CO2 building up in the Earth's atmosphere. Okay? So we have our own little mechanism through plate tectonics, which really helps keep things balanced in the Earth. Let's go back to Mars. Could we get a same feedback type process happening on Mars? Okay. Yeah, but only early in its history when the planet was more volcanically active. Okay. Right now, we do have volcanoes, and once in a while, there's a little bit of activity, but we need these volcanoes to really be spitting out a lot of carbon dioxide into the atmosphere. Okay. They're not so active anymore. In fact, we've never seen one have any activity. But early Mars had lots of volcanoes. Okay. Carbonates could have been added to the surface of Mars, which would have enhanced the amount of carbon dioxide through impacts. But one of the problems with carbon dioxide in the early history of Mars is that it may have not been able to keep Mars warm. Okay. Okay. Some of these charts are a little bit complicated, but if we go back, quite a long time, about 3.8 billion years, when we knew Mars must have been warm and full of water, the amount of energy that the sun was giving off was about 75% of what it was today. Remember, Mars already is receiving less than half the amount of sunlight that the Earth is. Okay? So if we look at the surface temperatures of Mars with carbon dioxide in the atmosphere, okay, where Mars was about 0.75 in terms of its luminosity, we're still well below the surface temperature we need to get liquid water. Okay? This is surface temperature in Kelvin, 220 degrees Kelvin. You think, oh, well, that's pretty good. That's 73 degrees colder than the freezing point of water. Okay, so calculations show that greenhouse warming through CO2 and HO2 could not have been enough to keep Mars warm. So we got a problem here. Why is it too difficult to warm early Mars? Well, first of all, we saw there's just not enough energy from the sun to take advantage of the greenhouse effect. Here's the other problem. Mars would have been cold enough where carbon dioxide would have condensed out of the atmosphere and brought much of this greenhouse gas, or rendered most of this greenhouse gas ineffective as it became locked up in the poles. Okay. Also, if carbon dioxide were to condense into clouds, carbon dioxide becomes a very good Rayleigh scatter. So the surface pressure, a higher surface pressure would mean that we'd scatter more light into space. And again, the reflectiveness of the carbon dioxide and the carbon dioxide clouds would have overpowered the greenhouse effect. So CO2 doesn't work for us, okay? CO2 by itself just doesn't do enough to keep Mars warm, okay? It's great at overheating Venus. I mean, Venus has got a crazy greenhouse effect going on, okay? Think about Venus, right? Hot enough to melt lead on the surface. It's even hotter than Mercury. But for Mars being in its position, CO2 wouldn't be efficient in the early atmosphere. All right. Again, Rayleigh scattering is why the sky is blue. We talked about this earlier. Shorter wavelengths of light are scattered more easily. Okay. Gives the sky its color. And carbon dioxide would have been, much more effective in scattering light. That's not what you want to have happen. You want the light to hit the surface and heat things up. There are some new theories about warming early Mars up. And, even from the time that some of these articles were published, computer models have actually improved our understanding. But there's a thought that not only would carbon dioxide play a role in heating the surface up, but also sulfur dioxide, which is a gas that is given off by volcanoes. So volcanic sulfur dioxide can build up when the climate is cold, similar to carbon dioxide. And when we look at sulfur dioxide, can sulfur dioxide give us a big greenhouse response? Basically, the problem becomes, and this talks about CO2 clouds, would need to be 100% covering the the planet in order to trap enough heat. And so, basically we're left with CO2 as a direct gas heating the surface. Doesn't work for us. CO2 clouds don't work for us. Okay. Even sulfur dioxide becomes somewhat of a problem for us. Basically, without dwelling on this too much, we just aren't able to, in all our models, to get the planet warm enough to get above the freezing point of water. Okay. So basically our models don't give us the answers that we want. What that means is basically the models don't predict what we've observed. We've got to improve on the models. And one of the ideas was not only using carbon dioxide and sulfur dioxide, nitrous dioxide, but I'm skipping through this because I think this atmospheric modeling is beyond what we should be talking about in an introductory course. But there was an interesting idea of sulfur itself in an unusual form, sulfur 8, and also amorphous sulfur particles from, again, volcanic eruptions, providing additional heat. So conclusion is this. I've gone through a lot of fancy atmospheric models and probably haven't talked about them in the depth that I need to explain what's going on. But, basically early observations of Mars's surface conclude that Mars was warm, okay? The amount of rainfall needed to carve out the Martian valleys far exceeds the amount that could have been generated by impacts, all right? But what we're missing is the mechanism to keep Mars warm, okay? We need everything in our toolbox to keep it warm. Carbon dioxide, nitrous oxide, sulfur dioxide, elemental sulfur, amorphous sulfur, okay? All of these must have played some role, but we can't get our models to produce a warm Mars, okay? But even though our models don't get us there, we're pretty sure Mars did have lots of liquid water on its surface, okay? What other conclusions can we make? We know the early atmosphere had to be plentiful. It had to be warm to support liquid water, but could still have the planet mostly covered with ice, although that would create an albedo problem. Current models say that carbon dioxide wasn't enough to keep Mars warm. Sulfur dioxide and amorphous sulfur from volcanism may have helped keep Mars warm. And this might explain why once the volcanoes became much less active, that Mars became much colder. But again, all this means is we don't have the model that works yet, so we have to keep working on these models. We'll get back to that. We'll get back to the hydrology on Mars, because when we talk about the exploration of Mars, that becomes a very big point. Okay, Mars is similar in composition to the Earth, but it lacks plate tectonics. It doesn't mean that's geologically inactive, though. We look at Mars. Mars has a core. Mars has a mantle. Mars has a crust. But the core of the planet, although it's very hot, probably is almost completely solid, all right? Why is that so? Well, radioactive decay is basically what heats a planet's interior, okay? So you got lots of energy coming from this radioactive decay deep in the core, okay? But as the energy is produced by this radioactive decay, all right, there's not a lot of radioactive decay. It has about the same number of radioisotopes as you'd find in a typical rock here on Earth. But the problem is, a rock here on Earth, that small amount of heat can't build up over time, but over billions of years, this heat takes a long time to escape out into space. Now, for a small planet like Mars, the rate that the heat can escape per unit volume is much faster than that on Earth. So Mars's interior is cooled off faster than the Earth. What does the interior look like? Well, again, we're sure that there's a metallic iron core, just like we have on Earth. This core is pretty hot, but under the pressures that it's under, it's not going to be liquid, okay? In the mantle, which is the layer above that, okay, this is dominated by a lot of mafic minerals, minerals that we find in things like basalt, or at least near the surface. Olivine and pyroxene are very common minerals in basalt. If you don't know what basalt is, that's that black rock that we see on Hawaii. If you go to the Palisades Cliffs in New Jersey, there are basalts, would I call them intrusions? I'm not a geologist, but they're definitely there. And then there's a light, low density crust on the very top, okay? Again, the core is heated by radioactive decay, just like what we have on Earth. But again, without a magnetic field, we can't know if the core was liquid or solid. We've had a magnetic field. Mars had a magnetic field. We know that the core was at least partially liquid. But without a magnetic field, we're pretty sure that that core doesn't really have any liquid volume to it, or if there's some liquid volume, it'd be very, very small, okay? The InSight probe, which we'll talk about later on, its whole goal was to measure how much heat is coming out of this core and making it to the surface. But unfortunately, its little mole that digs into the surface wasn't able to get very deep. So that type of measurement will have to wait for later, okay? What about the surface? The ancient surface of Mars, we look at Mars, we call it the red planet. That red planet comes from, iron oxide. I won't give you the oxidation state for red iron oxide because I'm pretty sure it's Fe2O3. Where it's for you chemists out there, it's Fe3, but I'm pretty sure that gives you the red iron oxide. But a lot of that's regolith. It's dust that's just been ground from rocks, and it covers the surface. That's responsible for those sandstorms. Here's what the surface looks like. And what we see is a lot of dark rock, okay? This dark rock is basalt. Oops, should use green. Basalt, which is a dark rock. And you also have quite a bit of red iron oxide dust in this regolith. Okay. We look at the surface, and most of the surface is comparable to an ultra dry frozen desert. What would be the closest to? The Atacama Desert in Chile is probably the closest to what the surface of Mars would be like. Again, there's very, very little atmosphere, so you wouldn't be able to breathe. But in the Atacama Desert, it's at a very high altitude, and there's a very low pressure. All right. So that is what's comparable there. Again, most surface is covered with this iron oxide dust, gives it the planet its orange-red color. Here's a better view of one of those basalt rocks. You can see the dark color of the basalt, which is generally a blackish rock. We have found some sedimentary minerals, but for the most part, the surface is really dominated by volcanic rock covered with this iron oxide regolith. Now, the surface history was pretty much put down in 3 different epochs: the Noachian, the Hesperian, and the Amazonian. I always laugh because the Amazonian is the really dry period. When I think of the Amazon, I think about this lush, wet rainforest. So I think that's sort of backwards. So if we look at the surface, everything in red here represents that warm wet period of Mars's history. Okay, all that material was put down long time ago. The Hesperian epoch is represented by the green, and then the Amazonian is represented by the blue. Okay, so we'll talk more about that surface history, and that's very much connected to the mission that the rovers are doing. Okay, yeah, let's go do that. The Nokian epoch lasted from about the formation of Mars, or at least when Mars cooled down enough that water could condense, to about 3.8 billion years ago. At this point, the land is dominated by impacts. Some of the impacts are filled with water. Okay, there's quite a bit of volcanic activity going on now. And this is the period of time where we're really interested in Mars, because we think this is when conditions were best for life. Okay, now I'm not talking about little green men or people walking around. I'm talking about life in the simplest sense, that maybe bacterial life could have arisen during this time. All right. After that, things started to dry up. Okay, again, whatever the mechanism was keeping Mars warm. Okay, things started drying up, and if Mars had a magnetic field, it's probably disappearing by this time. The Hesperian epoch lasted from about 3.8 to 3 billion years ago, and during this, many of the great lava plains developed. So volcanic activity is still going on. Okay, but for the most part, it's not to the same intensity that it was during the previous epoch. Although most of the water is now gone by the Hesperian, at least Valles Marineris would have shown, had some water. Okay, there is evidence that water was in Valles Marineris, which is the deepest canyon in Mars. Although small craters were still being formed at this period of time. No large craters would have been formed because basically we're way past the period of bombardment. And then finally, the Amazonian epoch, 3 billion years ago, still continues today. This is when there's still some geological activity, the great volcanoes, such as, and you can see it in this picture right here. Here's Olympus Mons. Here's some of the other volcanoes. Okay, all these volcanoes were built during the Amazonian epoch, but essentially the planet had dried up. So when we visit Mars, we try to visit places where the Nokian era would have produced the rock and the material for that time. Now, what do we know about this period? Well, one important aspect of this is that before things started drying up, the soil was still fairly neutral. Okay, it didn't become highly acidic like it did in the Hesperian period. So this would have been more conducive to life. Okay, you're still getting heavy bombardment, but this is when the valley networks would have formed. This is when the warm, wet Mars would have happened. Now, the next epoch, things are drying up. And as things dry up, the sulfates are producing very acidic environment. Even if life had formed on Mars, and even if life lasted into this period, it would have been a very difficult time for it. These would have been extremophiles, organisms that could bear extremely acidic water. Okay, but again, not as likely to see life in this period. And then finally, we get to the Amazonian period, from about 3 billion years to the present. You know, things are pretty dead now. If life had existed, it would have been almost impossible for life as we know it to continue in this period. Although some speculate that, very simple bacteria could still exist below the surface. And again, not only has the soil become very acidic, but pretty much all the water has left. And hydrous means without water. Ferric oxides, really no place where we'd expect life. All right. And again, the rock type that forms in each type has been very important to determining where we send missions. We'd like to look for clays on the surface. These clays, again, are thought to have formed in during the less acidic periods, whereas sulfates would have formed in a more acidic water. I mean, sulfates are evaporative rocks. Okay, they, many of them will form in the presence of water, but not the kind of water that we would think that would be conducive to life. Clays, those types of things form in more hospitable environments. And where all the red dust formed, that would not have been conducive to life. Here is another look at the surface in a different way. In addition to talking about the minerals on the surface, where again, just going back to this quickly, these reddish areas are indicative of clays. Okay, this is where we find clays. This green area is where we'd find sulfates. In every area, you'd find volcanic rocks because, Mars is very volcanic. And then here you'd find the anhydrous ferric oxides, the red dust, red rocks. In addition to the types of minerals present, we can see that Mars varies very much in its topography. We're going to talk about this region right over here. This is a huge volcanic plateau. All right. And there's a scar in it, and this is Valles Marineris. This is a scar that was probably created by a little bit of rifting. Okay. No plate tectonics on Mars, but that doesn't mean that we can't have the crust tearing just a little bit from rifting. And then you can see other areas. Here's an impact basin we'll talk about. And, another volcano out here. Oh, yeah, look, here's another impact basin. Actually, we'll talk about this low area in Mars, which continues to this side right here, maybe just one giant impact basin. You can see that better here. Look at this. It's like this whole part was pushed in. You see the backside of that too. Here's Hellas Basin. That is certainly an impact basin. All right. And here's Valles Marineris. Okay. And these is the Tharsis Plateau, which has a lot of volcanic activity and has Olympus Mons on it. Now, this area up here, this low area in the north, is known as Borealis Basin. This polar basin is thought to have been a basin created about 4 billion years ago. And if it's true, it would make the Borealis Basin the largest impact basin in the solar system. Okay. We know that when a large body hits another planet or moon, that we get, you know, well, in this case, we get a basin. When smaller things hit a planet, what I'm trying to say, we get craters. When massive things hit, we get a huge impact basin. And that's certainly what we see right here. All right. And this would fit in about a body about the size of Pluto, and would have, created a huge depression on that side of the planet. Okay. That's important because if we think about the Nochian period where life could have happened, that's before 3.8 billion years. So there's probably an extremely thin window between the time that this impact would have vaporized the entire surface and where life could have existed. Hellas Basin is a smaller but more likely impact basin. And it's about 2,100 kilometers across. Yeah, the Borealis Basin may not be anything. So, we can't say for sure that that was an impact basin, but the Hellas Basin was definitely an impact basin. Tharsis is a large volcanic plateau on the surface, sometimes called the Tharsis Plateau. And this is the largest geological feature on the surface of Mars. And it indicates that something's going on underneath. The first thing that we notice is, okay, we got lots of volcanoes. Olympus Mons, here's a volcano, here's a volcano, here's a volcano, tons of volcanoes. All right, that's fine. But the volcanoes are shield volcanoes. They only influence a small region around them. So Olympus Mons probably, created this elevated area. Now maybe some of this area here. Okay, this volcano maybe this much, this volcano maybe this much. A simple volcanic eruption cannot explain how this whole big area is so much higher than the surrounding regions. Okay, but we can explain it if we understand that Tharsis is perhaps under a huge mantle plume, which is pushing all the land up. Okay, this would make sense. When we see these large hotspots on the Earth, not only do we see shield volcanoes present, okay, we also tend to see the crust pushed upward. So Tharsis is probably a really good example of a mantle plume coming near the surface. And the other interesting thing is Valles Marineris, although there's quite a bit of erosion shown there, almost looks like a classic rift valley. It's being torn apart, okay? It's almost like this plume is pushing up, and like an overripe watermelon, it's splitting the planet at that particular area. So that's a very interesting feature to look at on Mars. Here's another view of Tharsis. Okay, and again, you can see the Rift Valley to the east and the volcanoes to the left, to the west. Here's a closer look at the 4 largest volcanoes on Mars. Olympus Mons is the largest volcano in the solar system. Okay. Ascrius Mons is, not quite as big, but certainly pretty large in size. Arsia Mons and Pavonis Mons represent, I don't know which one's taller than which. It looks like Ascrius Mons is the tallest. Arsia's would be number 3 out of all the volcanoes, and Pavonis would be the 4th largest volcano. So if I had to call them, I know Olympus is the tallest. I say this is second, this is third, and this is fourth. Okay. But yeah, they're the volcanoes, and these are shield volcanoes without any plate tectonics. These volcanoes can grow to very, very large sizes. The other thing is they're not like the composite volcanoes that we see out in Washington State. Like if you ever go to Mount Rainier has a classic composite volcano. It's very steep. Mount Fuji, the same thing. Okay, these are shield volcanoes. These things, if you look at them, have very gentle profiles. All right, you can see that here in this picture right here. That's a very gentle slope going down Olympus Mons. And here we see it surrounded by clouds. That's sort of interesting. And another view of Olympus Mons. All right. And interestingly, we don't think Mars is volcanically inactive. Basically because Mars had no magnetic field, we thought, oh, the core is cooled down, so there's not much heat that makes it to the surface anymore. There's big volcanoes, but those volcanoes are extinct. However, somebody got smart and started looking at the calderas, which are the center depressions in a volcano, and they imaged these things really up close, and they came to a really startling conclusion. Okay, we don't see any volcanoes erupting today, but that doesn't mean that these are extinct. In this region right here, which is highlighted, it can't be more than 140 million years old. Sounds really old, but remember the planet's 5 billion years old, because there aren't enough craters, okay, to indicate that. We can actually look at impact craters and say, well, this is how many impact craters we have, and therefore, this is how old this is. Well, there aren't enough impact craters there, okay? In fact, this region right here, this 3 region, numeral 3, that's 100 million years old. So volcanoes on Mars, first of all, they are big. How do they get big? Well, because there's no plate tectonics, hotspots never move. So once a hotspot forms underneath these volcanoes, they just get bigger and bigger and bigger. Here is what Mount Everest would look like next to Olympus Mons. Here is what the tallest mountain on Venus would look like. I can't remember its name, but clearly Olympus Mons towers over it. Oh, Maxwell Montes. Maxwell Montes are bigger mountains on Venus than we have on Earth by a little bit. But Olympus Mons blows those two out of the water. The name was right there, Maxwell Montes. Anyway, we even see volcanic mudslides, and this was taken by a high-resolution camera, indicating very few impacts. Okay, so this is 115 million years old, this mud flow right here. This one's only 25 million years old. This is 2 million years, 34 million years. So activities happen as recently as 2 million years, which is very young when we compare it to the total age of the planet. So although eruptions might be very infrequent, like once every 500,000 years, they do happen. Okay, so just looking at some different volcanoes again. Here, there's 3 that I showed you before. Olympus Mons is over here someplace. Here is Arsia Mons, which is actually this one right here. I just put a lot of images here because they're neat. Another view of Arsiamons in the Tharsis Plateau. Again, 130 million years ago was probably the last time we had a major eruption in Arsiamons. There's Pavonis Mons, Astrius Mons, and in Astrius Mons, as recently as 100 million years ago. Okay. And there's Valles Marineris, which again, here the volcanoes off to the west. So heat would come up and create these hotspot volcanoes. And as the plume would push upward, it would actually create this split in the surface, which was then eroded by liquid water. So Valles Marineris is the largest canyon in the solar system. It was once thought to be exclusively formed by erosion. Now it's understood to also be a rift valley. The dimensions are astounding. It's 4,000 kilometers by 200 kilometers and about 7 kilometers deep. If you want a perspective here, and I've been to the Grand Canyon, it just looks incredible. The Grand Canyon is only 277 kilometers long, 29 kilometers wide, and 1.8 kilometers deep. So this thing makes the Grand Canyon pale in comparison. And again, how does a rift valley form? Well, we get a hot plume from underneath pushing upward. It creates tension in the crust. The tension begins to pull the crust apart, and the floor of the valley actually sinks down, okay? And that's what creates this rift valley. So it's strange, this upward motion of this hot plume stretching the crust out creates a rift basin at the center of this. So the surrounding area is lifted up, whereas the rift basin is a depression within the surrounding area. And again, the original height of the basin might have been something like this. Also on the surface, we see erosion. There's a really cool satellite photo. I wish I'd included it in this, where you can actually see dust that's been kicked up from a recent slide. And what we think happens is there's water in the soil, and as the water moves, it does create some erosion, and it does create some landslides. So this mudslide due to subsurface ice still creates geological erosive processes. The poles of Mars are covered with a combination of water ice and dry ice. We would think about the polar areas as a large region of water which is frozen into the soil, a smaller region of water ice which is on the surface and creates white ice, and then on top of that you would have frozen carbon dioxide as dry ice. So what you're actually seeing here is sort of a combination of the water ice and the frozen carbon dioxide. These poles seem to fluctuate in size due to seasonal heating, as carbon dioxide freezes during the winter and sublimes during the summertime. And of course, the southern pole varies the most. Here's a view of the northern pole. We don't understand these spiral features, but they may be due to the periodic freezing and sublimation of the carbon dioxide. This image was taken from the Rosetta spacecraft. Actually, it looks like a Hubble image. On its way to an asteroid rendezvous. And the southern polar cap, as seen here, would have been 100% carbon dioxide, where the northern would have been a combination of dry ice and water ice. And dry ice has some weird properties to it. When exposed to sunlight, regular water ice produces what are called sun caps, but these little circular depressions are their own special type of caps in dry ice, and they always look like Swiss cheese, so they're not well understood. And again, look at the northern polar cap. During wintertime and during summertime, they're very, very different. Again, here's some more erosion on a crater wall, more mudslides. Again, this is a feature that we see near the poles, and look at these impact craters. They almost look like somebody threw a stone in a thing of slush. These flat structures might have been ice flows that could have formed before the water completely froze, and then it was covered with a thick layer of Martian dust. Would glaciers have formed? It would have required quite a bit of atmospheric pressure, but these look a lot like glacier scars. We're not sure what they are. But in any case, the surface of Mars is very, very interesting. It does have volcanoes, but the volcanoes aren't quite as active as what we have here on Earth. You know, there's always almost an eruption happening on Earth, whereas on Mars, the last eruptions that we can really pinpoint probably about 100 million years ago, but probably still have a chance of going on today. Let's look at missions to Mars. We have sent more missions to Mars than any other place. Our first flybys were in 1964, 69, and why do I have Mariner 4 there twice? Okay, Mariner 4, Mariner 6, Mariner 7. They were all sent by NASA. Mars 2 and 3, I think these were the Soviet Union. Mariner 9 went in 1971. And then a lot of our knowledge initially from Mars actually came from Viking 1 and 2, which landed in they were launched in 1975, landed in 1976. Okay. So the list that we see here doesn't include 30 missions that failed. So, and again, here's Mariner 4, not very sophisticated, but it took our first pictures of Mars, and it found that the surface didn't have any water, and the astronomer Schiaparelli drew pictures of Mars with what he thought were canals of water. So when Mariner 4 arrived, took pictures, and it looked more like the moon than this lush world. Astronomers were really, really disappointed. Again, Mars 2 was sent by the Soviet Union. It was the first to successfully orbit the planet, but its lander did not make it to the surface. Viking 1 and 2 were the first successful landers to the surface, and really gave us a lot of information about this planet. Even back in the 70s, these were state-of-the-art landers. So later exploration of Mars, we had Global Surveyor, which went by in 1996. Pathfinder and Sojourner. Pathfinder was a lander. Sojourner was a little rover. Mars Odyssey is an orbiter that's still in operation today, 20 years later. Mars Express, 2003, still working. Of course, Spirit and Opportunity were our first really sophisticated rovers that we sent there. Both Sojourner and Spirit and Opportunity were all powered by solar panels. So eventually they get covered with dust. Eventually they stop working. But Opportunity just stopped working, I think, in about 2018. It stopped working. Mars Reconnaissance Orbiter, 2005. Curiosity is still going strong. This is the rover that looks very much like Perseverance, and has given us a tremendous amount of understanding beyond what Spirit and Opportunity found. Maven's an orbiter, which has been very important to understanding the dynamics of the atmosphere, as we talked about earlier. ExoMars is an orbiter. InSight was a lander, landed near one of the polar regions. And it is monitoring seismic activity on Mars. But one of the instruments that wasn't successful, they're going to have this little mole that would drill into Mars and measure the temperature of the energy coming out. And of course, Perseverance just recently arrived. So that was 2021. Here's Sojourner. Sojourner was sort of a, let's see if this technology works, a little rover. And they got it to work. It landed on the Mars Pathfinder. So it was really a proof of concept type thing. But again, not very strong solar panels. Once the solar panels couldn't charge the batteries anymore, it died out. But it really showed proof of concept. After that, we sent more sophisticated things to Mars. This is the Mars Explorer rovers. They were named Spirit and Opportunity. And as you can see, they're solar powered. And they arrived on Mars in 2004. Spirit kept operating for about 6 years, and it finally succumbed in 2010. And Opportunity kept going along until 2018. And it succumbed, of course, very recently. But when you think about it, they were only designed to operate for about half a year. But yet they operated much longer than that. Why couldn't they go on forever if they had solar panels? Because as dust accumulates in the solar panels, they get less and less power, and they need this electricity to keep the rover warm. If things get too cold in the rover, like batteries, they fail, and then the rover basically ceases to function. And just getting an idea, Viking 1 landed right here. Viking 2 landed closer to the North Pole. All right. Pathfinder landed not far from Viking 1. Okay. So Spirit rover landed in Gusoff Crater. And the reason why we liked Gusoff Crater is we saw evidence of water flow into the crater. So we knew that water had been present there at one time. And why am I showing this again? I don't know. Both rovers landed near the edge of the Southern Highlands. Here's Gusoff Crater. And, I can never pronounce this properly. Meridiana Planum. So here is where Spirit was. Spirit. Here's where Curiosity was. Not Curiosity, Opportunity. And so there's Gusoff Crater, Spirit. And, took great pictures. Here we can see the basaltic rock, okay, and then some lighter colored rock right here. Here's a picture of Opportunity. Here's where it landed. It actually landed right in a tiny crater. And then, oh, it actually bounced, landed here and bounced into a crater and had to get out of there. And then it went and it explored this endurance crater right here. They called it Eagle Crater, by the way, because it was like hitting a golf ball on the first shot. And this is looking inside endurance crater. What they found are these blueberries. These blueberries are interesting. They're hematite, and hematite is a mineral that only forms in the presence of water. So we knew that this was very wet here. Hematite is iron oxide, so it was iron dissolved in the water, that when the water evaporated, they formed these little nodules. And here's a close-up of some of these blueberries. They're actually gray in color, but when they do a color enhancement, they look blue. And again, spectrometers told us that they were indeed made out of hematite. Okay. This is interesting. Was there standard liquid at one time? We see these, sort of interesting patterns, which may have happened when the water would go up or the water would go down, which was put on the rock. So what did we learn from Spirit and Opportunity? Well, we basically studied a lot of the mineralogy of the area. The climate in the past must have been warm and wet. Presence of methane, which was indicative of some type of either biological process, okay, which would be really exciting, it would have been proof of life, or abiotic process, such as some type of volcanic process. So in general, we studied the Mars's past. We found out, yes, indeed, water was present. In fact, we found evaporative minerals, and it really increased the likelihood that Mars was habitable for life at some time. Doesn't mean that life was there. Spirit and Opportunity were followed up by Curiosity. And Curiosity was launched in 2011. What you notice here is, instead of solar panels, this is powered by an RTG. RTG, radioisotope thermoelectric generator. And basically you have plutonium inside here, and the plutonium gives off heat. The heat is converted into electricity. The electricity powers the rover. Now you might think, oh, plutonium, this is a nuclear reactor. It's not a reactor. Plutonium, because it's radioactive, gives off thermal energy. It uses the thermal energy to create electrical energy, okay? So nothing as complicated as a nuclear reactor. Just we put something that's hot in there. The heat uses semiconductors to convert into electricity. Then electricity powers the rover, okay? You can see why we didn't use solar panels on this one. Look at all the dust that's accumulated on the surface. If the dust had gotten on to solar panels, it would have pretty much reduced the power given off. So this arrived in Gale Crater in 2012, and it was the most advanced rover to date, until Perseverance landed. And very sophisticated. I'm not going to go through everything. Like Perseverance, it has this mast that it has cameras on top of, has this robotic arm to take samples. Here's the RTG back here, and a number of different instruments to analyze samples as they come in. And just to get an idea of the size, this always cracks me up, because Curiosity and Perseverance are basically the same size. So don't be upset that I didn't include Perseverance here. But here's tiny little Sojourner, okay? Not very big at all. In fact, Sojourner is about the size of the robotic arm complex at the end. And then we get to the bigger Spirit and Opportunity. And then here's Curiosity, okay? So this thing, Sojourner, was about the size of a toy, okay? Bigger than a remote control car, but, you know, not really huge. Probably about the big as a suitcase. Spirit and Opportunity were, you know, about golf car size. And then Curiosity and Perseverance are about the size of a compact SUV. And here is where Curiosity's been. It started right here. Here's its landing point. And it's gone along, and all along the way, it takes samples of material. It had to avoid, these are sand dunes, by the way. Okay. And after it went down here, it was looking at this was 2019, so it's actually further along here. It looked at this clay bearing material, which was very important in terms of, this was put down about the time that Mars was still wet. And then up here you have sulfate bearing material, which will be more along the Hesperian period. So, you know, Curiosity's still going. I mean, it's still performing its experiments and still going along, and it's traveled here. It's traveled quite a few miles. There's a kilometer for scale. And as it does so, it takes samples and analyzes those samples. What it can't do is store the samples. So what did Curiosity find? Well, like Spirit and Opportunity, it found evidence of persistent liquid in the past. It detects a suitable environment for life in the past. That the minerals that are present pretty much indicate that, yeah, bacteria could have lived in this type of environment. Interestingly, it found organic carbon in Mars rocks, but we're not quite sure where the organic carbon came from. Found that methane is being produced by something and being dumped into the atmosphere. Unfortunately, the amount of radiation that's on the surface of Mars now is pretty significant. And Curiosity basically has determined that the high level of radiation could be very significant in terms of the health for future humans on Mars. Okay. And of course, it confirmed that Mars at one time had a much thicker atmosphere and more water was present on Mars. Perseverance landed in February 2021. It's approximately the same size as Curiosity, but it's a lot heavier and much more advanced. Again, Perseverance is doing much of the same work that Curiosity did. It's looking for past environments capable of supporting at least microbial life. And it's also looking for signs of microbial life that may have fossilized themselves into the rock. What it will do, it will cache samples, it will collect the samples, store them, and then put them on the surface for later retrieval. The other interesting thing that it's doing is it's an actual experiment to try to see if oxygen can be generated from Mars's atmosphere. Finally, this is the coolest part. It's going to fly a drone, a little helicopter drone. And this is really a demonstration of technology. Much like Sojourner was trying to demonstrate the technology of a rover, okay, this little tiny thing called Ingenuity, this little helicopter, is going to try to see if we can send future drones to Mars to explore it. And again, here's just looking at the different landing sites. Here's Viking 1. So these sites were explored in the 70s. There's a Phoenix lander up here. InSight is right here. So those are just landers. Those aren't actually rovers. And then as far as the rovers go, why don't they have, oh, Pathfinder, there's Pathfinder. Pathfinder and Sojourner were the first lander rover combination, then Spirit and Opportunity, okay, then Curiosity, and now Perseverance. So you can see we're doing pretty good as far as doing pretty well, exploring the surface of Mars, all right? We're looking all over the place, and we're trying to see what Mars was like very early on. Here is where Perseverance is going. And again, this is looking at all of Mars. There is this Acidus Basin, which is an impact basin. And on the edge of this is the crater known as Jezero crater. So that's where Perseverance landed. Okay, landed right in there. And great place to look because that's where carbonates are located according to the spectral analysis that we've been able to do from orbit. And again, that's the exact landing spot right there. Okay. And this is the edge. Here's the edge of the crater, by the way. Oops, wrong tool. Here's the edge of the crater. Okay. So we're sort of off to the side of the crater. And again, it will be exciting to find out what it discovers. I did another presentation on Perseverance. So if you want to know what all of these different instruments do, I encourage you to watch it. And Ingenuity, as we said, will be the first drone to fly on a different world. Mars's moons, at this point, we don't think they're very interesting. They're very small, they're regularly shaped, and many people still believe that they were captured asteroids, okay? They look like potatoes, really. And I didn't give the best images here, but not thought to be active, not large enough really to have much of a significant gravitational field. But what's interesting, we may use Phobos and Deimos as sort of landing places where we could stage, missions to Mars, and it actually make a lot of sense to, first, stage equipment on Phobos and Deimos, and then because you get trapped in the gravitational well, send missions down there from there. Phobos is doomed because of its orbit. Gravitational tides bring it closer and closer to Mars all the time. This is the opposite effect that our own moon has. Our own moon is moving away from us. Phobos is moving closer to Mars and will eventually be torn up by gravitational tides before it falls into the atmosphere. Have we discovered life on Mars? Well, a long time ago, we thought we did. We thought this sample of Mars was filled with fossils of bacteria. Now you're going to go, whoa, what are you talking about? Sample of Mars. How do we get a sample of Mars? Okay. Well, the interesting thing is we've identified this meteorite as being blown off the surface of Mars. And because it traveled to Earth, we have a sample of Mars. However, this conclusion that these represented little microfossils is not well supported. We think that they're just, inorganic processes that produce this, but that would have been really cool if this famous meteorite was our first sign of life. Okay. So summary of Mars, last of the inner planets. It was once warmer and wetter at one time. About half the, clear. We know Mars is about half the size of the Earth. Why does it keep picking the wrong tool? So half the diameter of the Earth and about 11% of the mass. Okay, so quite a bit smaller than the Earth. Most of the water we believe escaped into space or froze into the soil. We are pretty sure it may be volcanically active, but at a very, very low rate. Could have supported simple life at one time, and it only has two moons, Phobos and Deimos. I think Phobos was the god of fear, and Deimos, one was fear and one was something else. But in any case, Mars was the god of war. Phobos and Deimos were supposed to be his sons, which were fear and hate or something like that. Not so nice for them. Okay, that concludes our presentation on Mars.